So here in 2.3, we're going to talk about another way that we can do inference, another way that we can do a type of significance test. So significance testing is the same thing as hypothesis testing here. Basically, we're going to be given a situation where somebody has a certain hypothesis, and we're going to test whether or not it is true or it is false. And all the hypotheses that we'll be testing in this section will be just about the means. We'll talk about how to do different types of hypothesis tests for other types of statistics in sections later on. For right now, we're just looking at means though. So with hypothesis testing, there is a very specific order that we have to do things and a very specific set of things we have to include when we're doing this. So this 4-step set of notes right here is super important that we follow every time we're doing a hypothesis test. The first step when we're doing a hypothesis test is we have to state what the hypotheses are, and there are two. There's a null hypothesis and there's an alternative hypothesis. So our first step to hypothesis testing is we actually need to tell what those two hypotheses are, and we have to actually talk about them in context of the problem. That's pretty standard with everything that we do in AP Stats. Whenever we talk about any numbers, even if we give the correct symbols, we have to describe what it means in context. So like if you were talking to somebody who knew nothing about what mu stands for, describe to them what is actually occurring. All right, once we have those two hypotheses written down and we've described what it means, we're then going to state the type of hypothesis test that we're going to perform. In this section, the test that we're going to be working with is called a z-test. There are other tests also that we are going to learn about, but for right now, we're going to focus on just one, which is the most common one we will be using, and that is a z-test. After we just state the test that we plan to use, we also need to justify any of the conditions or the assumptions that need to be known about our distribution in order for us to be able to do that kind of test. Okay, so for a z-test, the one thing we have to know for sure is true before we start is that we're looking at a normal distribution. We've talked lots of ways about how we can confirm whether something is normal, using the central limit theorem if we need to and things like that. But we have to state that in our second step that it is normal and we have to give a reason why. Step 3, once we've met those conditions, we can then compute the actual test statistic. A lot of times that will be given to us. That would be our sample mean in this case. Statistic is spelled like so, statistic. Anyway, so we compute the test statistics. Since we're doing a hypothesis test for means in this section, the test statistic would be a sample mean. And we use that sample mean to calculate our associated p-value. And p-value is the same thing it was in the last section. That's the probability of our hypothesis being true, actually. And then lastly, once we've got our p-value, we can give our conclusion. And just like in the beginning, we want to make sure we write our conclusion in context of the problem. You can't just write yes or no or true or false. You have to explain what it all means. So when we get to that conclusion, there's actually only two possibilities that we can write for a conclusion. In the end, we can reject hypothesis, but we can never accept it. So our goal here actually is to reject the null hypothesis. If we can reject the null hypothesis, then that supports the fact that the alternative hypothesis may actually be true. Again, we cannot say for sure that either of the two hypotheses are true. We can simply prove that one of the two is not true. So when we choose our alternative hypothesis here, and actually I should say first, our null hypothesis, which we write H naught for null hypothesis, is basically assuming that there's nothing out of the ordinary happening. Okay, so for this example down here with this AP Stats teacher, this is the distribution of all the AP Stats scores for the entire nation in 1997, and this is what the mean score for her students was. You can see this 3.45 is generally much higher than this 2.97 here. So her hypothesis, which was going to be our alternative hypothesis, her alternative hypothesis is that her class of students is much better than the nation as a whole. So they're gifted students, in other words. So our null hypothesis, again, going back to that, our null hypothesis would be that she is wrong, right? It's what we want to disprove. So our null hypothesis would be that her class is no better than the rest of the nation. So the average is not any higher than the nation average, 2.97, or it's not significantly higher. So we would write our mean is equal to 2.97. Even for this class of seemingly gifted students, we're saying 3.45 is not significantly greater than 2.97. So that's our null hypothesis. Our null hypothesis will always be that the mean is equal to the population mean, and there's nothing out of the ordinary happening here. Our alternative hypothesis, then, we're going to go ahead and look here and say maybe this is out of the ordinary. We have three different kinds of alternative hypotheses that we can have in a hypothesis test. Two of them are one-sided, and the other one is a two-sided hypothesis. So with our class of supposedly gifted students, we're looking at this type of hypothesis right here, where we're thinking that this class of supposedly gifted students, their scores are up here at the higher end of our distribution, and therefore their average is more than usual. It's statistically significant that it is more. So we're going to look at z being greater than a certain value here. Our hypothesis, our alternative hypothesis for this type of situation would look like our mu is greater than some value. Okay, and then on this end, of course, you can see it's the same thing happening, but now it's on the lower end. So I would say my alternative hypothesis is that mu is less than the population value. Okay, so depending on what's the person or group of people is claiming, what they want to claim, that's what we're going to look at here. Okay, and then we have our two-sided hypothesis. We'll see this in a bit after we get through these first few examples. A two-tailed hypothesis, you can see we're looking at either end being far away from our mean. And the way this looks is like this. Here we would have our alternative hypothesis is that the mean is not equal to the population parameter, meaning we're not saying it's strictly greater than or it's strictly less than. We're only saying that it's simply not anywhere close to the actual mean itself. It's really far from the mean in either direction. But in these two-sided hypotheses, the direction isn't really significant, so it can work either way. Obviously, the probability of the size of our probability in these situations is going to be much larger than the size of our probability in these situations. So it'll actually be harder to disprove a null hypothesis using a two-tailed alternative hypothesis. So if I can prove, or if I can reject a null hypothesis, using a two-tailed hypothesis, then I would say that's even more significant than it is on a one-sided. Okay, so let's go back to what we have here though. And this one we're being very specific that she thinks her students are not just different, but that they're better than average. So our alternative hypothesis is that her class's mean is greater than the population mean. Okay, so there are my two hypotheses there, but again, we have to talk about this in context of the problem. I can't just leave it like that. Okay, we do like to have it written like that with our symbol so it's very clear, but we also need to describe what does this mean, okay? So the first part here, we'd say our null hypothesis is that the class of students is not the class is right side the classes test scores are not statistically, or significantly is the word I want, significantly different from the national average. Okay, we already know they're not going to be the exact same. We already know that their mean is 3.45, which is definitely greater than 2.97. So we're not saying that. We're just saying in our null hypothesis that 3.45 in that case would not be statistically significant, significantly different from that 2.97. Okay, and then of course our alternative hypothesis is the opposite of that is true. So our alternative hypothesis would be the class's test scores are significantly different, significantly higher. Are significantly higher specifically. Different would mean two-sided. Significantly higher than the national average. So our goal here is that by disproving the null hypothesis, because the alternative hypothesis is the exact opposite, that would mean the alternative hypothesis is likely to be true. Okay, so that's step one. Now step two, I have to state what type of test we're doing, and I already said the only type of test we're going to do for this section is a z-test. So the way I write this, I say we will perform a z-test. Okay, if I was doing a different type of test here, I would just state the name of that test. We're doing a z-test here. And when I say that I'm going to perform a z-test, I also want to talk about what significance level I want to choose. We've talked about significance levels in the last section also. Our significance level is basically kind of like a margin of error in a way. It's how close, how sure do we want to be. So we talked about before, our significance level could be 0.05 or 0.01 most of the time, meaning we are either 95% sure or we are 99% sure of our answer. Of course, it's going to be harder to prove things with a 0.01 significance level than it would be to prove things with a 0.05 significance level. And being 95% certain is still pretty dang good. So most of the time out of these two, we actually do end up choosing a 0.05 significance level. We would really only choose a 0.01 significance level if it was super important that we did not make a mistake. If we needed to be absolutely almost completely certain that something was true, then we would want a 99% confidence or a 0.01 significance level. Okay, but again, for the most part, unless the text or the question or the problem says to choose a 0.01 significance level, you should pretty much just always use a 0.05. Okay, but we should know how to do both, of course. So back to what I was writing, we will perform a z-test with a significance level. Since they don't say what to use, we'll do 0.05 of alpha equals 0.05. Okay, so that sentence alone is just the type of test I'm going to perform. The significance level is part of the name of that test, basically. Okay, the other part of step two, though, we also need to confirm that all the conditions for performing a z-test are met. And the only condition that has to be met here is that we have to ensure that we're looking at a normal distribution. Okay, so looking back at our data here, I believe in the actual problem on Apex, it does say this is for sure normal. The shape of this curve definitely does support that as well as what we see down here. So I'll say because the problem states this is a normal distribution. Okay, so there my condition is met. I wrote that down explicitly, and now we can go ahead and perform our z-test. So there's actually a lot of ways that we can approach the test itself. There's a way to do it on our calculator. There's a way to do it just using all the different probability methods that we've already talked about. There's some numbers we can memorize to make things faster. So I'm going to start by showing you the way that we can do it full out, not skipping any steps, not using our calculator at all. Okay, so this is called a z-test because the first step to performing a z-test is I'm going to take this score here, 2.97, and I'm going to calculate its z-score. Okay, remember a z-score is a standardized value for a normal value in a standard normal curve. So we're taking this value from this normal distribution and we're going to change it so that it's now in a standard normal distribution, which means that the mean will be at 0 and the standard deviation will be 1, right? So to calculate the z-score, remember you take that value, 2.97, subtract, or not the value, the statistic value, whoops, our test statistic. We're going to take this value, our test statistic, which we're trying to use to disprove our null hypothesis. So we take our test statistic, subtract the population mean, and divide by the standard deviation. And remember here, we're looking at a distribution of sample means. So the standard deviation for the distribution of sample means is always the standard deviation of the population divided by the square root of the sample size. Okay, that is in your formula sheet. We need to recognize when we have to use that. So on the denominator here, I'm going to have the standard deviation of the population divided by the square root of the sample size, 25 students. So when I put this all into my calculator, I get that the z-score for 3.45 is 1.80. Okay, so now that I've calculated I had my test statistic was 3.45. I calculated the z-score for that. Now I can go ahead and calculate my p-value. And where p-value means probability of. So we want to find the probability of this being true. The probability of mu being greater than 2.97 using what we just got. So we have this z-score now. So we want to find the probability, the probability of z being greater than 1.80. Okay, and we've calculated probabilities of z-scores taking on certain values lots and lots of times in this class. We can use any of those methods here to do this. So I could do this with normal CDF on my calculator. I could do it with normal CDF on my calculator, even just using 3.45. We didn't actually have to standardize it to find that probability, did we? It's just part of the process of doing a z-test, though. Okay, if we can't use a calculator, though, I would use my standard normal table. And that's going to happen a lot of the time here. So let's go to our standard normal table real quick and talk about that. So we're going to look at our standard normal table for the probability of z being greater than 1.8. Okay, and I know I already have it kind of on here, just talking about it. Okay, so here's 1.8. 1.80 has this probability of being below. So this standard normal table only gives us the probability that z is less than or equal to that number. So in order to get the probability that it's greater than, we have to do 1 minus that value from the table, 9641. And so when I do that, we get approximately 0.036. Go back to my worksheet now, my notes, and say this is about 0.036. So that is our p-value. And at that point, we're basically done with step 3. Okay, as I said also, there's more than one way to get that p-value. So another thing I want to talk about before I even do my conclusion is this table over here. So with this table, we have some numbers that basically give us our general boundaries for our standard normal table all the time. So we went ahead, after we got that the z-score was 1.80, I took it over to my standard normal table and found that probability of being greater than that. Okay. So the thing is, the standard normal table never changes. And if we're looking at a 0.5 significance level, the z-score that we need in order to be statistically significant is never going to change. That's what these z-scores here are. At a 0.05 significance level, for a one-sided test, we need our z-score to exceed this value in order to be statistically significant. So we had positive 1.8. 1.8 is greater than, it's further from 0 than 1.65. Therefore, it is statistically significant. Okay, looking up here at the actual p-value I calculated, p-value was 0.036. 0.036 is less than the significance level that we chose, 0.05. So that also tells us that this is statistically significant. Okay, memorizing this number 1.65 right here is helpful because then we can save us from having to calculate the probability by hand. Is that necessary? No, it's just helpful. So with this table here, we have all of our boundaries that make things truly statistically significant in all cases. So looking at a one-sided test like we just did, 1.65 on the positive end or negative 1.65 on the negative end would give us something statistically significant. If I wanted to change my significance level to 0.01 instead, you can see we would need an even greater z-score for that to happen. So these are called our z-stars or our critical z-values. In fact, I'll write critical z-values. So you can openly refer to these critical z-values and use them to justify your answers in your answers, and statisticians will know what that means, okay? So these are the critical z-values for each of our significance levels for one-sided and for two-sided tests. So we'll look at a two-sided test next also. So let's go ahead and talk about how I'm going to write my conclusion now. So with our conclusion, we said because our z-score was higher than our critical z-value, or we could say because our probability of our z-score being higher than that was lower than our significance level that we chose, we know that this is a statistically significant situation. Her students really are gifted. The probability of having a class of 25 students with an average score that high is very little. It's only a 4% chance of getting a class that size with that high score. So she does truly have a gifted class. So how do we write that? We say, okay, well, since we have to kind of give a reason, our p-value 0.036 is less than our significance level, alpha, which we chose to be 0.05, we reject the null hypothesis. Okay, and so that's what we have down here. If our p-value is less than alpha, we reject the null hypothesis. And remember, that's what we wanted to do. We wanted to reject the null hypothesis because that supports the alternative hypothesis, which is that her students are gifted. Okay, if the p-value was actually greater than alpha, meaning it's more probable to happen, then we would not be able to reject the null hypothesis, which basically means our results are inconclusive. If we can't reject the null hypothesis, then we can't do anything. We can never accept the null hypothesis, okay? We either reject it or we don't reject it, and that is it. So there's our conclusion. I need to, though, state it in context of the problem. Super important. So what does it even mean that this is significant? It means that her class is gifted. So we say this means that this class does, or may actually, we don't know for sure. You can't say for sure. We only rejected the null. We didn't accept the alternative, but it is definitely plausible. This means that this class may be better than average, than the average statistics class. Statistic. Okay, my goodness. And there we go. Now I have my conclusion stated not only in statistic world numbers, but also in context of the problem. So we are done with that question. Yeah, there's a lot to write in here. You will definitely see a question asking you to do a hypothesis test like this on your AP exam in the free response though. We will do a lot more of these in the future also, so you will definitely get a hang of it. Okay, one more thing I want to show you about this problem, and I know I spent a lot of time on this problem, is this orange part here, the actual calculating our test statistic and p-value, performing the z-test. I told you there's also a way to perform the z-test on your calculator. Of course, you already know I could have calculated this p-value using normal CDF in my calculator, but there's also a way in our calculator that I can do this entire test using just my graphing calculator, and it'll even give you a picture. So let me show you how that works. Okay, pause. All right, so I just wanted to make sure real quick that my calculator was all set up and ready. So to do this z-test completely on your graphing calculator, you're going to hit the stat button here and go over to test. And the very first one that I see on mine is the z-test. I think it might be the second one down on some calculators, so be careful. So if I choose the z-test, you have the option to put in either data or stats. So with the data option, you can see this third thing down says list. So I can actually put all of my data into list 1 or any list here, and it'll do a z-test on a whole set of data. Okay, but we don't have the raw data here. We don't have the individual test scores of these kids. We have the stats. We have their sample mean, okay, which is right there. Make sure you guys can still see what I'm doing. All right. So I'm going to go over to stats and hit enter. And now I'm going to put in everything we have. So going down, what is our null hypothesis or the population mean? 2.97. 2.97. Enter. What is the standard deviation of the population? It was 1.33. 1.33. What is the sample mean? 3.45. 3.45. And N, what is the size of our sample? We have 25 students. 25 students. And then lastly, you can see here's our different options for our alternative hypothesis. Do we want a two-sided hypothesis? Do I want to determine if our sample is less than the population mean or that it is greater than? And we want it to be greater than, didn't we? So I'll select that one. And then going down, I have the option to just calculate it, or I have the option to draw it. And I like the draw option. It'll still give you the actual answer, but it gives you a nice picture to go with it, which is a great thing to sketch on your exam to get more credit. So I'll hit enter. It's going to draw my normal curve, and it shades the area that represents the probability of our value being higher than 3.45. And it tells you right here my z-score 1.8 that we had calculated before, as well as the p-value that we calculated, 0.0356. So all of those numbers, as well as a nice picture to go with it, just with a few clicks of a calculator, and super simple. Again, we can't use a calculator for all portions of our exam, but when we can, this is a great thing to include. All right, so moving down, now we're going to do a two-sided hypothesis test or a two-sided significance test. They are the same thing. This one we have a factory that produces light bulbs, and the mean life of the light bulbs that they create, they want it to be 1,000 hours. Okay, it's really important for companies, especially companies that mass produce things, that they can say with confidence what the efficiency of their product is. So their efficiency, they say it lasts for 1,000 hours. Okay, and they have a standard deviation of that for 50 hours, quite a bit. So when they do a um, a, a test here to see how they're doing. They took 25 bulbs and tested them, and the mean of those bulbs was 982 hours. So they're concerned now that their 1,000 hour life is no longer accurate. So we're going to test that for them and see is 982 is still fairly close to 1,000. So is it statistically significant that it's not 1,000, or is it close enough that it's okay? So they asked us to perform a significance test at the 0.05 level. So we start by writing our hypotheses. H naught is that the mean is equal to the population mean, and HA is that the mean is not equal to the population mean. And I'm choosing a two-sided test here because they don't specifically say whether they're concerned for it to be greater than or less than, simply that it's not equal to it. Okay, and remember, a two-sided significance test is harder to prove because it's easier for that p-value to be large when we're looking at two sides of the graph. So if they don't state left or right or greater than or less than or give some indication of that, you can pretty much assume a two-sided test is the way to go. So I do have to put in context of the problem. I'll say this one is that the mean bulb life is 1,000 hours, and this would be the mean bulb life is not 1,000 hours. All right, and then we move on to stating the test that we're going to use. Of course, we're going to use a z-test because it looks to be normally distributed. It even says right here, assume normal distribution. So I'll go ahead and write my condition first. I don't have to write it a certain way. I'll say, since we have a normal distribution, there's my condition. Okay, I don't have to put my condition last. I can put it first. We will perform a z-test. With a significance level at 0.05 because that's what they told us to do. Alpha equals 0.05. There we go, step 2 done. Now I can go ahead and calculate my perform my z-test and calculate my p-value. Okay, so again, I will do this by hand and then I'll do it again with my calculator so you can see how that looks. So to do my z-test, I need to calculate the z-score at our test statistic, 982 hours. Subtract the population mean, divide by the standard deviation of the sampling distribution for the mean, so that'd be the standard deviation of the population, divided by the square root of our sample size. There was 25 bulbs sampled, and that gives me a z-score of, I don't think I have it on here, of negative 1.8. Negative 1.8. Okay, so then I can use that negative 1.8 to calculate my p-value, probability that z is not equal to negative 1.8. We would actually calculate it as being we would want 2 times the probability of it being, let's see, negative. Our mean on our standard normal distribution, remember, is at 0. So the negative 1.8 would be over here. So we're looking at this tail in this case. So we would want z to be less than negative 1.8. I also do want to include this upper tail as well, which is going to be the exact same size as the lower tail. So to get both, rather than looking at below negative 1.8 and above positive 1.8, we can simply just multiply that probability by 2 because those tails will be equal. Okay, so I could use my standard normal table to find that value, or I could also look up here and say, okay, I memorized these numbers. That's the only way you're going to have is if you memorize them. And if we're doing a 0.05 significance level for a two-sided test, if our z-score exceeds negative 1.96, then it is statistically significant. Well, is negative 1.8 further from 0 than negative 1.96? No, negative 1.8 is closer to 0. So this is not going to be statistically significant. We are not going to be able to reject this null. In fact, if I continue here and get this p-value, the p-value ends up being, let's see, I didn't have it actually calculated here. So I'll go ahead and look at my thing. Standard normal table, negative, that's the first page, negative 1.80 is right here. So that's below that, which is exactly what we want to, 0.0359. And then I double that to get my other tail as well. And you should get, let's say, what is that, negative, no, not negative, positive. Grab my calculator real quick. 2 times 0.0359 is 0.0718. So there's a 7% chance of getting a light bulb that's around that value. That's pretty high. It's definitely higher than the 0.05 that we chose. So again, we're not going to be able to reject this null hypothesis. So 0.0718. Oops. Okay, so again, that number is greater than our alpha we chose, 0.05, so we cannot reject the null. Okay, so there is nothing here to suggest their light bulbs are performing, or their factory is performing at a, I don't know if it's, there's no reason to be concerned about this statistic here. It's not so different than from 1,000 that we should be concerned about the life of these light bulbs yet. Okay, and again, I can get those same numbers, the negative 1.8 and that positive 0.0718 using my graphing calculator. Let me show you that. All right, so I'll go ahead and turn this on, clear that out, go to the stat button, tests, z-test, we're still on stats. Our new mean is 1,000. Our new standard deviation is 50. The sample mean was 982. And the size of our sample is 25 again, but now we have a two-sided test. And again, I like to hit draw. Calculate just gives you the number. Draw gives you the numbers as well as a nice picture. So there's my two-sided picture, my z-score negative 1.8, and the p-value 0.0719, exactly what we had. So I'll go back to my notes. All right, and we simply just need to state our conclusion now, okay? So I like to state my conclusion the same way every time, no matter how I go about it. I like to say, since our p-value was not, in this case, not less than our significance level, alpha, which was 0.05. In this case, we cannot reject the null hypothesis. So what does that mean in context of our problem now? That means that this sample does not indicate that the light bulbs are have a life statistically different, significantly different from what they should be, basically. So let's see. We believe that the sample does not indicate that the light bulb life is, I can't say higher or less than because it's a two-sided, so I'll say significantly different. So significantly higher or lower. Different from the average of 1,000. Okay, I'm not accepting that it is 1,000. We're just saying we can't really say much at all. Okay, if we don't reject the null hypothesis, our results are basically inconclusive, and we say there's not really much to worry about at this point. All right. Moving on, we basically the videos in Apex, they go over these problems a couple extra times, talk about some different things with them. So I wanted to give you some space to work for the most part. So I'm not going to write stuff on all of this. You're welcome to when you're looking at the videos, if you have extra things you want to write, use this space. But I do want to talk about a few things here. So the first one, going down to this last one, the last time they talk about the light bulb factory, they actually changed this 982, oops, to a 975. They say, okay, so they do these quality checks pretty often in factories. So every time they do the quality check, they have to determine if the difference in results is statistically significant. So this time they do the same thing and they get an even lower amount of hours for the lifetime of these light bulbs. So we need to do it again. So on this one, I'm not going to write it all out, but let's do our z-test again. So if I calculate a z-score from 975, the same way that we did before, this time you get a z-score of negative 2.5. Negative 2.5. Okay, so from here again, I can calculate the p-value, two-sided p-value for negative 2.5 in my standard normal table, or you can try to remember those numbers. Those critical z-scores. Negative. We have a lot of stuff going on here. We have a two-sided significance test at the 0.05 level, which means we want to get a number that is further from 0 than negative 1.96. So let's, oops, that's not what I want. Negative 1.96. Okay, the z star at 0.05 is negative 1.96. So negative 2.5 is further from 0 than negative 1.96. So this is statistically significant. Our p-value is less than 0.05. So we can reject this null hypothesis. Okay, so simply changing from 982 to 975 was enough to make this a problem. Now they should be worried about their light bulb life, and they should be making adjustments to their factory so that their claim of 1,000 hours is still accurate. Okay, and again, if I use my graphing calculator here, this should be super quick because I actually already have the numbers in there. Just need to change the 1 to 975. And you can see now we have, there's my z-score, negative 2.5, and the p-value is definitely less than 0.05. In fact, it's almost less than 0.01. So this is statistically significant. We reject the null, which means that their average light bulb life is not what it should be. Okay. For the rest of this, study portion, it talks about how hypothesis tests are very similar to confidence intervals. In fact, we can make the same conclusions using basically the exact same numbers by looking at a confidence interval rather than performing a hypothesis test. So to do that, we have this class of 40 seniors with a GPA with an average GPA of 2.75 and the standard deviation being 0.4. And we want to use the confidence intervals to determine if this group of high school seniors and their GPA being 2.8 is statistically significant. Okay, so we can do this problem using a hypothesis test or a significance test. But here we're going to show you the confidence interval does the same thing. So let's start by calculating the confidence interval, just like we've done before. So we'll do both. They ask for both. So I'll start with 95%. And then we'll do our 99% confidence interval also. And remember, the only reason why one of these intervals is more confident than the other is because this 99% one is going to include more values. So of course, we're going to be more confident about a larger interval containing a certain value, because the wider net catches more fish, right? So for the 95% confidence interval, we take our mean. It's always, I'll write that up here so you don't forget. Remember, it was mean plus or minus our z star times the standard deviation, which for the sampling distribution of the sample means, that would be the standard deviation of the population divided by the square root of n, right? That's how we get our confidence interval. We've done this before. So let's see what we get here. Our population mean is 2.75 plus or minus the z star for a 95% confidence interval, or alpha 0.05, is 1.96. The standard deviation of the population is 0.4. The sample here is 40 students. So we subtract to get our lower bound, add to get our upper bound, and there is our 95% confidence interval. That means, again, that we are 95% confident the true mean is within these two numbers. Okay, and then for 99% confidence, we do the same thing with a different z star. Remember, the z star, the critical z value for a 99% confidence interval, or alpha, is 0.01, was 2 it's on the last page here, 2.56. Yes. No. 2.58. Oops. Can't read. 2.58 times same standard deviation. Okay. So we subtract to get our lower bound, 2.6. Add to get our upper bound, 2.9. So here we are 99% confident that the true mean is within these two numbers. So moving down to the second part of this, actually down here, use this confidence interval to test the belief at the 95% confidence level that the mean GPA for all high school seniors is actually 2.8. So the 95% confidence interval that we just calculated above was this. So is it possible that this is the true mean GPA and it is in fact not 2.75? Well, since 2.80 is within the 95% confidence interval, right? 2.8 is between these two numbers, is it not? That means there is a possibility that it could be the true mean. So, within the 95% confidence interval, it is possible that it is the true mean. All right? Okay. So I think that's all that I need to put on here. Again, feel free to make sure you watch that Apex stuff and add whatever else notes you need to do. Or I guess I suppose I could do this one last example on this page. Okay, so one more example, we're going to do a two-sided hypothesis test and show you that it's going to give us the same result, same values actually, as doing a 95% confidence interval. So here it says, during the month of October, the produce department of a local grocery store has historically sold an average of 250 pounds of apples a day, with a standard deviation of 62 pounds. The produce manager wants to know if this has changed. So we want a two-sided, not greater than, not less than, but simply different. He randomly picks 70 days in the past 5 Octobers and calculates a mean of 283 pounds. Test the appropriate hypothesis using a hypothesis test with a significance level at 0.05. Test the appropriate hypothesis using a 95% confidence interval. Okay, so starting with the hypothesis test. Step 1, state your hypotheses. H0 is that the mean is the same as it has always been, 250. The mean, or the average, actually is a more user-friendly term, huh? The average apples sold in a day is 250. And then our alternative hypothesis, the produce manager wants to know if this has changed. So he wants to know if the mean is not equal to 250 anymore. He's not worried about being less or greater, just that it's different. So our alternative hypothesis is that the average apples sold in a day is not 250. Okay, and then we state what type of test we're going to do. Does this say that this is normally distributed? It does not. It does not explicitly say that this has a normal distribution. So how could I say for certain? Well, n is 70. Okay, if we have a reasonably large, greater than 30 sample size, that should be enough to say that this is normally distributed. I'm gonna have to pause for a second. All right, so like I was saying, since our sample size is relatively large, it's greater than 30, we can say that this is approximately normally distributed based on the central limit theorem. All right, so since our sample size is large, the central limit theorem, CLT, says our distribution should be normal. So we can do a z-test, okay? Remember, we can't just do a z-test without verifying that we have a normal distribution. That's the condition or the assumption we have to make. All right, so since our sample size is large, the central limit theorem says our distribution should be normal, so we can perform, or we will perform, a z-test with significance level alpha equals, and do they say, yep, they say to do a 0.05, so I'll do 0.05. All right, so then we move on to step 3, calculating our test statistic. That was already done for us. Our test statistic is that X bar is 283. So then we need to calculate our z-score and our p-value. So let's see, we'll say z equals, and if I want to, I can even do some little graphing calculator magic on here real quick. Stat, test, z-test. It was 250 apples a day. Yeah, 250 apples a day. Standard deviation was 62 apples a day. The mean was 283 for the sample. And this is a sample of 70 days. We want a two-sided hypothesis test and draw. So there we go. Z is 4.45, which is what I got when I did it by hand. Oops. Where'd it go? There you are. So Z ended up being 4.45. And our p-value was 0. Okie dokie. Okay, so I can talk about that. So our p is approximately 0. Obviously, nothing is impossible. So it's very, very close to 0. It's probably like 0.0000000 something. And the calculator rounded that to 0. So why is it 0? Is this really impossible? Our z-score is 4.45. That's 4.5 standard deviations away from our mean. So we're saying this is highly improbable to have. So we definitely have enough evidence to reject our null hypothesis here. Give me 1 second. All right, so our conclusion is that since our p-value 0 is less than our significance level, alpha 0.05, we reject the null. So what does that mean in context of the problem? That means that the alternative hypothesis is likely to be true. So the average apples sold per day, going back to my alternative hypothesis up here, just kind of restating it actually. And I will not say it is, I say, well, it is not likely to be 250. And that's it. So that is our hypothesis test. So now we're going to see if we can get the same results with the same information using a confidence interval instead. So it says test the appropriate hypothesis using a 95% confidence interval. This is all the same data they gave us above. Before you set up your hypothesis, we just did all this. Well, that's what we all just did. So coming down here, computing our confidence interval now. So confidence interval, X bar was 283. That was his sample mean. We're going to add and subtract to that. Our Z star for a 95% confidence interval is always 1.96. And the standard deviation for a sampling distribution is the standard deviation of the population, 62, divided by the square root of the sample size, 70 days. So when I subtract, we get 268.48. And when I add, I get 297.52. All right. So is that significant? So our H naught was that the mean was 250. So can I reject that null hypothesis here? Well, 250 is nowhere within our 95% confidence interval, which means we're 95% confident that that is not the average apple sold per day. We're 95% confident that the average is truly within these two numbers. So yes, we can reject our null using this confidence interval. So 250 is not within this 95% confidence interval. So we can conclude in context that the true average number of apples sold per day is not 250. Exact same conclusion, different approach. Okay, so all of this is getting to the same conclusion. It's just different ways to go about it. So making sure that you know how these two procedures are related is going to be super helpful in the long run. And that's it for this section.